And as I said, we'll start from scratch. So we'll start from a template, the mechanical millimeter template, and just create a new drawing from this. All right, so let's get started on this first exercise, which starts with creating a cylinder first. So in the solid tab of the ribbon, under the primitive tool, I can find the cylinder icon. I will just place it in the origin of my drawing. I'll use a radius of 70 millimeters. And a height of 16 millimeters. Now I'm going to use the offset tool to create this smaller circle on top of this face here. To do this, I will first make sure I have the face selection enabled so that I can highlight the face, and then using the quad on this top face under the Draw tab, I can find the offset tool. And I will create an offset of 25 millimeters from the edge here. So 25 and enter. So as you can see here now, a circle was created. I will now push, pull, or extrude this circle so that a hole is created in my cylinder. There's two ways to do that. I can either enable boundary detection and just move my cursor inside the circle so I can highlight the boundary and then extrude this boundary downward to create a hole in my cylinder. Or if I undo this, I can do it another way, for which you don't need the boundary detection, so you can simply highlight the circle itself and extrude it downward to create the hole. Now, let me open the mechanical browser, because we start from a simple new drawing. We haven't done anything parametric yet. The mechanical browser is still empty. So I will create three new parameters to drive the shape of this cylinder here. I can either right-click this node here and click Add New Parameter, or in the ribbon under the parametric part here in any of the tabs, or most of the tabs, you will find this Parametrize section here. You can click the New User Parameter button. I will do this 3 times. So 3 new parameters are created in the mechanical browser. I can rename them and give them values, so I can either select them one by one and under here, under parameter, enter a name, like let's say, change the name to D and the expression to 140. Or if you want it done a bit quicker, you can use a shortcut. If you're on Windows, you can select this parameter here and hit F2 on your keyboard, and you'll be able to rename it and also give it a value. So this second one I will rename to D5 equals 58.1. And then this second one here, B equals 16. So it's a bit faster than I have to click here in the name and expression field. Now, to make sure that my cylinder always stays flush with the XY plane, I'm going to add a fixed constraint to the bottom face here. So fixed constraint. And then I will also add a distance constraint between the top and bottom face so that I can manage the height of the cylinder using a parameter. So distance constraint between this face and this face. So now I have my distance 2. I want this to be governed by my parameter B here, so I can simply change the expression here from 16 to B, which now means if I change the value of B, distance 2 will change, and so the height of the cylinder will change. I can also animate the parameter to check this, just to be sure. Okay, 2 more parameters to add here, or two more constraints to add. There's the inner and outer radius of the cylinder here. I can add a radius constraint to this inner one here and press enter, and then the same to this outer one. I'm going to link these again to my existing parameters here. So this is the inner radius, which has an expression of 45. I will change this to be the half of d5 here, so d5 divided by 2, and radius 4 will be the main diameter, d divided by 2. So just to check, I can select my parameters here and animate them to see what each one does. All right, I'm going to add some holes now. And instead of modeling the holes directly into my solid, I will add them as objects, really, as components. So I'm going to open the library panel. And under holes, there should be this standard circular hole feature. And I can just place it on top of this face here. Make sure your dynamic UCS is enabled so you can place it accurately. As you can see, there's 2 input fields. I'm going to use these two to accurately place my hole. So the first one here, I will enter 55. And I will hit tab to go to the second one. And I want this to be aligned with the x-axis, so 0. And press enter. Now, going back to the mechanical browser, I will see now that this one hole has 2 parameters, so the diameter and the depth of this hole. I can simply select, let's say, this depth, and in the expression, make sure it links back to one of the global parameters. So these are local parameters of this hole, and these are global parameters in my drawing. I want this to be linked to my global parameter. So depth, I will set equal to B, so that the depth of my hole is always equal to depth of my actual entity. And I can do something similar for diameter. Well, actually, I want to create a new parameter, a new global parameter for this diameter of the hole in my drawing. So I can either, again, just create a new parameter, give it a new name, and then link this name to this parameter here. But actually, it's a bit easier to just right-click this parameter and click link to parameter. So it will link it to a global parameter. If there's already an existing parameter here with the same name, it will be linked to that automatically. If not, it will create a new one. So in this case, this parameter is called diameter. There is no existing diameter parameter here, so it will create a new one for me. Now I can rename this one to say, for example, thread. And it should still be linked. So if I now animate my thread here in my global parameter, the hole will change. I'll give it a value of 12. And now that we have this hole, we will create an array from this. So I want to have more than one hole. To do that, I will go to the solid tab here, or actually in the home tab, I can find it as well. There's the polar array button here. I want to create an array of holes, so I will select my hole here. I want to have the center of my array to be in the center of this face here, so I can just simply click snap to the center. And I'll just press enter to accept all the default values for this polar array. Now I want to make sure that the array is properly aligned with this entity here. So I want to add an extra constraint to make sure that if my cylinder becomes thicker or thinner, that the holes also move with it. To do that, I will create a new distance constraint. And instead of selecting the holes themselves, I will go into the block sub option of the distance constraint, which will mean that I'm going to lock or I'm going inside the coordinate system of the block that I select. So in this case, it will be the array. And I'm going inside the UCS, or the coordinate system of this array. And in this case, I will choose the XY plane as my reference entity. And I want this to be linked to the height or the top face of my cylinder here. So I select this one as my second entity. And I will just accept the default value. Now this distance constraint is displayed here among my other constraints, but I don't want to change the value anymore. I want this to always remain the same value. So I will just make sure it's not exposed so nothing can accidentally move it or change it. All right, let me just now turn off the subtract layer so I can see the holes more clearly. And now going to mechanical browser again, I'm going to add two new parameters that will govern the radius of the polar array and also the number of holes. So again, adding two new parameters. One being the number of holes. I will just call it n and give it a value of 4. And then the second being the diameter of the polar array, which I will name k and give it a value of 110. And now scrolling down here in my mechanical browser, I will see this one polar array of holes. I can see that it has a bunch of parameters. Again, these are local parameters, much like we had the hole earlier. And we want to link these to the global parameters of my drawing. So for instance, the radius, I can rename or give it an expression, namely k/2. And the number of items, in this case 6, I will change it to be equal to n, which is 4. So you should see also the model change when changing this to n. Now I notice it now has 4 holes, but it's not really symmetrical. It's because the angle between my items is still not, it should be linked to the number of items, of course. So that should be 360 divided by the number of holes, which is n. So now if I change my number of items, if I change this to, let's say, 10, it will still be evenly divided. All right. So we're almost done creating this component here. So I will click the root node of my mechanical browser here, this component 1. I will actually also give it a new name. Let's say Flange. And I will also denote this entity or this component as a standard component. You will then notice if we later insert this into another drawing or an assembly, this component will be denoted as a standard component. Much like this hole, for instance, is also a standard component. It's denoted by, it's a different icon and a non-standard component. Let me just check some of these parameters and see if they behave correctly. So I'll just animate them. Inner radius, height, and the thread diameter. It looks correct. And now I'll just add them to my library. So to do that, I'll open the library panel again. Let me just go back to the home tab here. So I'm back in the home menu. And I'll click this blue plus icon to create a new component. So adding a new block to the library. In this case, I will just select the entire drawing to be this block or this component. I'll give it a name. I can create new category or choose one. I already have one in this case called the demo. And I will just click create. So doing that, inside this demo folder, I should now have this flange component. So just to check if everything works, I can just open a new drawing and insert this flange. Let me just place it somewhere random here. And in the properties panel, I can find all of these parameters that we created earlier, and I can change, let's say, the value of the outer diameter to something else. So that seems to work fine. Okay, so I'm again going to start a new drawing based on the mechanical millimeter template. And I'm going to insert the flange that we just created. So from the library, we can go to the folder that we used and just click the flange to place it. I will put it just in the center here at the origin of the drawing, 0, 0. Now I'm going to add a gasket and another flange on top of that. I don't have them in my library yet, but I can simply insert them from the starter files. So again, in 18 design tables, under starter files this time, you will see 2 more drawings. We'll start off with the gasket. And we can simply drag and drop the gasket into our model, which we'll call the BM insert command, which is what we need to insert this component. So I want to insert this component here so that the bottom face of the gasket is flush with the top face of the flange. The easiest way to do that is to enable dynamic UCS, and when hovering over the top face here, hit the shift key so it's locked, and I can move it freely about in the same plane, and then simply snap to the center of this face. If you don't have the center snap, you can enable it under E-snap here, and enable center. Now, currently the gasket is not yet constrained or linked to the flange, so I will add some constraints. First of all, I want to make sure that both the flange and the gasket remain concentric at all times. So I can do that by adding a concentric constraint here. And I'll select the inner radius here, or the inner face here, and the inner face here to make sure that they're concentric. But now they're still not really fixed together because I would still be able to move, let's say, this bottom part down. It's not fixed yet together. So I'm going to do that as well using a coincident constraint and make sure that the top face of the flange is always coincident with the bottom face of this gasket. So to select this bottom face, you'll have to use the tab key to cycle through it because you cannot physically see it. It's not directly in your line of view. So hit the tab key once until the bottom face of the gasket is shown. And now they're basically glued together. So if I move one object, the other will move with it as well. We'll do the same with the second drawing here. So there's another blind flange that we can, again, just drag and drop into our drawing to insert. And I will use the same technique. So with dynamic UCS enabled, hover over the top face of the gasket, hit the shift key once to lock the plane, and then snap to the center. And again, I will have to add similar constraints because now this top part is not yet linked to the rest of the model. So again, a concentric constraint between, let's say, these two faces here, and a coincident constraint between the top face of the gasket and the bottom face of this blind flange. So the bottom face I can see here. And the top face of the gasket, again, I'll have to use the tab key, just kind of guessing where it is with my cursor and hitting tab a few times until I hit this top face here. I can always check them again in the mechanical browser by selecting them and seeing which faces are highlighted. So now in the mechanical browser, I have 3 subassemblies here, all of which have a bunch of parameters. Now again, these are local parameters for these inserts. We don't have any global parameters yet. I showed you before that you can create global parameters by creating them manually here, or by linking from local parameters into your into the global drawing. So I will do actually just that. I will just select all of the parameters from this first flange here, and all in one go link them to global parameters. So they will create new global parameters here that are linked to this entity or the instance. And I will do the same for the others here. So link to parameter and link to parameter. Now you'll notice that before I do that, actually all of the parameters, the parameter names here already exist in my as global parameters because they're the same names as the one in the first flange. So it will take those values. So notice that as soon as I link to parameter, you will see some changes in the model because they're updating according to what the existing values of the parameters are. And this now means that because the parameters of the blind flange and this first flange that we created, because they have the same name and we linked them to the global parameter, they're also, of course, aligned. So there's now 4 holes in both of them, and so on. Now, we now have these 7 parameters governing different things in my drawing here. So maybe I can take a look at what everything does. For example, the height of my flanges, thread thickness here, or the global diameter. But all of these are now still able to be manipulated one by one. So I can change the diameter, change the thread, change the number of holes, but they're not linked in any way. Also, I can choose whichever value suits me. So I can say, okay, the diameter of this flange should be like 152.64897, which is not realistic because mostly we will use rounded values. And to make sure that a user who inserts this assembly into a drawing does not have this full freedom, we can use a design table. A design table, there is a design table in the starter files of the exercise. Let me just open it and show you what it looks like. It's basically just a CSV file. And it has a bunch of columns and rows. I'll load this. Now this design table was set up so that it fits the parameter names that we used in our assembly. So you see this D5, D, BK, and all these same names that we know from our assembly. And basically, it gives you preset values for all these parameters grouped together. So this first column would be the name of your setup, and linked to this this setup here are these parameter values. So you have to make sure, of course, that the names in your CSV file are correspond exactly with the names in your mechanical browser here. And if that's the case, I can create a new design table from File, select my CSV file. And now you notice that all of these parameters have been put into the design table because they have the correct name that corresponds with the CSV file. Also, this one we didn't have yet, but it was part of the CSV file. So it's now also part of my design table here. And this now means if I select my design table here, I now have the choice between all of these preset values, which correspond to this first column in the CSV file. And changing a value here will change all of the values of these parameters according to this design table. Now there's one final thing that we need to do for this assembly. That's to add some bolts. Again, I'm going to use standard parts here from the library. I can go to standard parts here, fasteners, bolts, or I can just simply search it. Actually, I'm going to do that. It's going to be easier. Search for DIN 933 and click it. And before placing it, I will actually change the size to something smaller. So let's say M12. So this one here. And place it in one of the holes. Again, hover over the top face so it's aligned. Hit the Shift key to lock the face and then snap to the center like so. Now going back to the mechanical browser, I will see this hole again has a couple of parameters. There's a part number which is governed by size and the length. I will actually link this size to parameter, but before I do that, I will just show you that there is already a size parameter in my design table, as was specified in the CSV earlier. So when I link this value to a parameter, it already has this parameter, so it will link to this value of the design table. And I will also do the same for this length. We don't have parameter yet for length, so when I click link to parameter, it will create a new global parameter for me, as can be found here. And I will change this expression to be something so that we always have a rounded value or a multiple of 10 millimeters. So I'll do that by typing in round b times 2/10 times 10. So I will always have a multiple of 10 millimeters close to the actual double thickness of the flanges, so twice this b value. Okay, and now I again will create a polar array, so similar as we did for the holes. I will use a similar technique, so create a new polar array, select my entity, select a center point. I'll just press enter for the default values. Again, we need to make sure that this new polar array is linked or is constrained to the rest of my assembly so that it doesn't move. So I'll do the same technique using distance constraint. Choose my XY plane and the stop face. So now it's properly constrained. Again, I will make sure that my distance constraint here is not exposed because I don't want to change it. And then finally, I need to make sure that the parameters of my polar array are also linked to my global parameters. So if I go to my polar array here, there's again these parameters here. So these things like the radius and the items. And I will again, like with the holes array, do the same. So the radius should be equal to k/2. And the number of items should be n. And the angle should be 360/n. So now everything should work properly. The entire model should be coordinated. So if I make a change to one of the global parameters here, not only the number of holes, for instance, will change, but also the number of bolts. So I can check that by changing, let's say, the value of this design table here to something else. And that seems to work fine. So now we have a full assembly with 3 sub-assemblies and some bolts. And again, I can create a new component from that to use further in a larger assembly.